Good afternoon and all. I am R.V. Kiran, Assistant Professor, Department of Mechanical Engineering. Today in this class, I am going to explain you about the instantaneous center method. In the previous class, I have started about the instantaneous center. So what is an instantaneous center and what are the types of instantaneous center and how it is located. In today's class, I am going to explain it deeply through the instantaneous center method through different examples. And this is my 30th lecture regarding to the subject kinematics of machinery. So in the previous classes, we have discussed about the instantaneous center. So the instantaneous center is the method of analyzing its motion between the two rigid links. One is movable, another one is the rigid one. And types of instantaneous center methods, that is fixed, permanent, and neither fixed nor permanent. And we have explained the three types. And we have discussed about the location of these instantaneous centers and properties of instantaneous center. And today I'm going to explain about the velocity analysis, that is the instantaneous center method. So, in this instantaneous center method, the motion has a complex type. So, the motion is a complex type of motion in such a case of pure rotation. So, when there is a pure rotation in the motion, it is a complex one. That is, it is a tough one. But compared to the remaining types, that is the remaining types of the instantaneous center, this is the complex one. And as the position of the link AB goes on changing, so does the center. So this is the link AB. So AB is the link which is transferring to the motion to A1 B dash. Sorry, that is A1 B1. So that is the final link stage of the link A B. So okay, finally we are going into the A1 B1. So here this link is going to revolve or move it in the dotted lines portion, and finally it is used to oscillate. So does the center. So the center of the position is the A link, and it is used to move in the B side. So as the position of the link AB goes on changing, so does the center about which AB is assumed to be rotating. So this AB is assumed to be rotating. So here we can see the rotation of the AB link. So it is rotated in the second motion, that is the B side, and it is fixed on the A side motion, that is A side motion is fixed. So it is moving on the point B. So it has a new point as B1. So about which AB is assumed to be rotating. Hence, the name instantaneous center is called in the A position. The locus of all such instantaneous centers is known as centroid. So we are locating the centroid here. So the centroid is named after the locus of all the instantaneous centers. So locating the instantaneous center itself in the locus position is defined by the centroid. And next, a line drawn through an instantaneous center and perpendicular to the plane of motion is an instantaneous axis. So the line drawn through the instantaneous center, which is the perpendicular line out to the plane of motion. So this is the plane of motion here. So B2 B dash and A2 A1 is the plane of motion here. So we are drawing a line perpendicular. So this is the line perpendicular to the axis. So in the second diagram also you have seen that A1 B1 is perpendicular to the original line AB. So this is the line perpendicular to the original line AB. So we are locating these centers to the perpendicular to plane of motion. So the locus of the instantaneous axis is known as axode. So the combination of the axis plus centroid is called as axode. So this location of the line drawing through an instantaneous center, which is perpendicular to the plane of motion, is an instantaneous axis, and the locus of these instantaneous axis is known as the axode. Is known as the axode area. So axode means axis plus centroid. So the definition of the axode is axis plus centroid is called as axode. Next, locating an instantaneous center of rotation and its use. So what is the use of the instantaneous center of rotation and what is the location? How are you locating these instantaneous center of rotation? So first of all, there are two direction of velocities in this diagram. So you can see the velocity of A, which is in the x-axis direction, and velocity of B, that is in the y-axis. So velocity of B is in the direction of y-axis. So these two velocities are perpendicular to each other, and the line which is connecting these two links, that is the link AB, is angled towards the 30 degrees, and from B also it is angled towards 30 degrees, and we are generating a point Q which is perpendicular to both the points and locating it at the Q position, which is at right angled position. So here you can see the right angled position of the point Q from the points A and B. So from the 2 points A and B, we are locating the instantaneous center of rotation. So just two directional velocities help locate the ICR. ICR means instantaneous center for the rotation. So that is the shortcut for the instantaneous center of rotation. And then one complete velocity. So that is when you need to complete a velocity, you need to have the magnitude and direction. So both magnitude and direction in the complete velocity and one other velocity of direction. So this helps in the finding the velocity of any other point. So here you can see the velocity of A is defined as 4 meters per second. So velocity of A is defined as 4 meters per second, and velocity of B is not given. So this velocity of A is sufficient to find the velocity of B. That is, both magnitude and direction have been given here for only one point. So other direction of the point can be easily varied. So one complete velocity, that is magnitude plus direction, and one other velocity direction. So one other velocity direction helps find the velocity of any other point. So this helps in the velocity of finding any other point. So this type of location of the instantaneous center is found in the example here. So in the first picture, there is no velocities in the both the velocities. So there is no magnitude and direction. But in the second picture here, you can see the velocity of A is given, that is 4 meters per second, and velocity of B is not given. So that is clear here. So then we are going to find the velocity of B from the given intentions, that is the angle given to A to B, and next the velocity of A, and in the direction which is perpendicular to velocity of A. So these are the combinations. So by finding it, velocity of A by A O, so that is not Q, that is O. Velocity of A by AO, that is velocity of A by AO is equal to velocity of B by BO. So that is the perpendicular, two perpendicular lines is equal to angular velocity. So whenever we having the three velocities, so it is defined by the velocity of A by AO, that is equal to velocity of B by BO, that is equal to velocity C by CO. So these three velocities have been given, and the three perpendicular directions also have been taken, which is equal to the angular velocity of the motion. So this is the procedure for locating an instantaneous center of rotation. Here I have taken a simple example for it. So locating two velocities with the one velocity is known, other velocity is not known. So that is the only one. So next one is the velocity analysis for the locating an instantaneous center of rotation. It is here I am taking the plane motion of body, and its combinations. So first of all, from the previous slide, we know that velocity of A by AO is equal to velocity B of B by BO, that is equal to the angular velocity. So this is the diagram in the previous slide. So I have taken the plane motion of body here. I am taking the plane motion of body regarding to the. So we are taking the angular velocity with respect to the angular positions. So first of all, I am taking the velocity of A. So here, this is the velocity of A direction, which is equal to the x-axis. And I'm taking the velocity of A cos alpha. So the cos alpha is taken in the x direction as well as the perpendicular direction also. I'm taking the VA cos alpha. So the angle between the A and B link is alpha to the velocity of A direction. Next, I'm taking the velocity of B, that is towards the perpendicular direction of velocity A, that is in the y-axis direction, but not equally to the y-axis, but it is perpendicular to the x-axis. So that is taken as velocity of B cos beta. Velocity of B cos beta. And next, we are taking only the velocities of these directions, that is velocity of A and velocity of B. So taking it in the both directions, it is obtained as cos beta by cos alpha. So it is obtained as cos beta by cos alpha. So it is obtained as sin 90 minus beta by sin 90 minus alpha. So it is obtained as cos beta by cos alpha is equal to sin 90 minus beta divided by sin 90 minus alpha. So we get the sin 90 minus beta by sin 90 minus alpha. So it is taken as instantaneous center for the A and instantaneous center for B. That is AI by sin 90 minus beta and sin 90 minus alpha. So in total we get the value velocity A by velocity of B, that is instantaneous center of A by B. In total we get the value as AI by VA by AI is equal to VB by BA, that is the angular velocity of the omega. So here we are considering these plane motions regarding to each other. So that is the plane of motion of each one. So next one is the instantaneous center. So that is locating the number of instantaneous centers. So here you can see the number of possible combinations of the two links. So that is number of possible combinations of the two links and number of combinations of n links taken two at a time. So taken two links at a time. So number of instantaneous centers is equal to number of possible combinations of the two links, and that is equal to number of combinations of n links taken two at a time. So that is we are taking two number of links here, and therefore we get the combination as capital N is equal to n into n minus 1 by 2, where small n is equal to number of links. Small n is equal to number of links. Then less number of instantaneous centers. So we are going to find the number of instantaneous centers positions here. So first one is the fixed instantaneous center and second one is the permanent instantaneous center. So you all know about the difference between the fixed instantaneous center and the permanent instantaneous center. So in the figure you can see the it ones. So the ABCD quadrilateral is the fixed instantaneous center. That is the instantaneous center location. And these I13 and I24 are the, so these I13 and these I24 are the neither permanent or nor fixed locations. So it is in the neither permanent nor fixed locations. So the blue color one is the one. So in the fixed permanent instantaneous center method, it remains in the same place for all configurations of the mechanism. But in the permanent type, it changes the position, but the nature of joints is same. But the nature of joints of the positions is same, but it is neither fixed nor permanent. So generally, it is neither fixed nor permanent. So these are some of the examples for the location of instantaneous centers. That is the rules for the locating instantaneous centers. So when the two links have a sliding contact, that is when the two links have a sliding contact, the instantaneous center for the rotation lies on the common normal at the point of contact. So that lies in the common type of contact. So first one you can see the for two links. So there are two links attached to it. For two links connected by a pin joint. So these are the two links. Sorry. So these are the two links, and this is connected by a pin joint here. So this is the pin joint. So which is located on the center of the pin. So this is located in the center of the pin. And next one is the, it has a pure rolling contact. So there is no slipping in it. So it has a pure rolling contact, and the instantaneous center of rotation lies on the point of contact. So it lies in the point of contact. And third one, that is the instantaneous center of the rotation lies at the infinity position, and each point on the slider has the same velocity. So it has the same velocity on each point. And fourth one is the curvature. So curvature, and it has a body which is attached to it. So curvature and a body which is attached to it. So the instantaneous center on the center of the curvature. So that is on the center of the curvature. So this is the instantaneous center for both the points A and B. So it is in the center of the curvature, and which is of the curvilinear path at that instant. So at the point of instant, it lies in this curvature. And last one, lies on the center of the curvature. So the instantaneous center of rotation lies in the center of the curvature, which is being the center of the circle, is fixed for all configurations of the links. So that is fixed for all configurations of the links. So these are the different rules and different sections of the instantaneous center. Next one is the this instantaneous center is based on the three centers in line theorem, that is the Kennedy's theorem. So from the Kennedy's theorem, we know the formula n is equal to n into n minus 1 by 2. That is capital N is equal to small n into n minus 1 by 2. That is, we are taking it as 3 into 3 minus 1 by 2. So in total, we get the value 3. So the number of links for the theorem is 3. So here I am only stating the statement of the theorem only. I am not explaining the full theorem. In the later sections, I will explain the theorem. So these Kennedy's theorem states that if three bodies move relating to each other, they have three instantaneous centers and they lie on a straight line. So they definitely lie on a straight line centers. And the instantaneous center of BC, that is the intersection point of AB and AC, that is BC, must lie on the joining of AB and AC. So that is the locating center of the instantaneous center. So here I am considering instantaneous center for BC lying outside the line joining AB and AC. And now BC belongs to the both the links B and C. So you have know that it is belongs to B and C links only. And next, we are considering the instantaneous center for the BC, that is link B. So link B, and velocity of BC must be perpendicular to the line joining instantaneous of AB and instantaneous of BC. So that must be perpendicular to the line AB and BC. Next, we are considering the link BC, that is which is link C, and it must be perpendicular to the line joining IAC and IBC. So it is perpendicular to the line joining IAC and IBC. So this is the two links from the Kennedy's theorem, which is has a unique point, and hence regardless of the whether it is the link B or link C. So whether it is link B or link C, it should have a unique velocity, that is both in both magnitude and direction. So it has a both magnitude and unique direction, and this is possible only when the three instantaneous centers, that is namely IAB and IAC and IBC, so which lie on the same straight line. So these, they are going to lie on the same straight line. So this is the instantaneous for the three links, sorry, 3 points, that is three joints, that is IAB, IBC and IAC, which lie on the a straight line, which lies on a straight line. So next one is the rules providing this instantaneous center method. So first one, determine the number of instantaneous centers by using the relation. So we are locating the instantaneous center by using the relations of it. So that is n is equal to n into n minus 1 by 2. And next, make a list of all the instantaneous centers in the mechanism. So make a list of all the instantaneous centers and then locate by inspection the primary instantaneous centers and mark them by solid lines on a circle diagram. So in the right side picture, you can see the circle diagram there. We are going to mark it on that. So locate by inspection the primary ICRs and the market, and next the locate the secondary instantaneous centers by using the Kennedy's theorem. So we are going to locate the secondary instantaneous centers using the Kennedy's theorem. If three bodies move relative to each other, they have three instantaneous centers and they lie on the straight line. So these lie on the straight line. So to implement these, look for the quadrilaterals in the circle diagram. So here the quadrilaterals is ABCD. So ABCD is the quadrilateral position. You can see in the four bar mechanism, the pin jointed four bar mechanism, in which AD is the fixed joint, in which clearly each diagonal, that is from 1 to 3, will form two adjacent triangles. So it forms the two adjacent triangles. So this is the first triangle and this one is the second triangle. So this is the first and this is the second triangle to it. So then instantaneous of center of 1 3 will lie on the intersection. So that is, it will lie on the intersection of 1 2 and 2 3. So that will lie on the 1 2 and 2 3, in which three bodies, that is 1 2 3, and the instantaneous center of I14 and I13. And from these, the three bodies, that is I34 is produced if necessary. So that statement will pass it to the I24 also. So I24 and I13. So these are the two elements in which it got three elements, I14, that is I212, I23 and I34. For the I24 position, it got one I12, I14 and I23, I24, which is produced through it. So these are the, and next one we are going to find the angular velocity in that. So angular velocity of AB is given in this diagram, and omega of AB is given, and omega of BC and omega of CD are to be determined. So these are to be determined in this section. So we are going to the stepwise procedure of the finding of this angular velocity. So step one is the, it got perpendiculars to the two known direction of velocities of B and C, which help to locate the instantaneous center for the rotation at O. So we are going to locate these instantaneous center at O position. So by extending this position, we got the O position. So by extending AB and CD. And next, step 2 is point B belongs to both. So point B belongs to both the positions, and the link AB under pure rotation above A. So AB is the link here. It is used to rotate in this direction. So that is about the pure rotation. And next, the link BC, which is under complex motion, is equivalent to pure rotation above A. So that is in complex motion, which is about pure rotation about A. Next, step 3, it is the point C belongs to both the link CD, which is under pure rotation about the D, and the link BC, which is under complex motion, which is equivalent to pure rotation above O, which is about the pure rotation above O. So therefore we got the values omega of AB into AB is equal to omega of BC into BO. That is omega of BC is already known by now, and omega of CD into CD is equal to omega of BC, that is omega of BC into CO. This is the extension of the CD line, and BO is the extension of the AB line. So therefore we got these two values by getting the procedures. So by this, I am ending this class. In the next class, I will explain some more examples, problems. We are going to implement it. Thank you.